Okay, you guys, so this is just a quick video on how to find the nth term. I'm going to do some problems from the Discovering Geometry book, and then I'm going to go into more general terms with some examples. Okay, so to begin, gives us a couple examples. Now, these aren't necessarily an arithmetic or geometric or quadratic. These are just problem solving, right? So given lines passing through the same point, okay, called concurrent, into how many regions do 35 concurrent lines divide the plane? Okay, well, let's look. So if there's one, it divides the plane into two spaces. And if it's two intersecting lines, it divides it into four. So I'm going to write 4. And if there's 3 lines, it's 1, 2, 3, 4, 5, 6. Okay, let's try the next one. So let's go. Here's 1, 2, 3, 4 lines. And that would divide it into 1, 2, 3, 4, 5, 6, 7, 8 spaces. Now, if I just draw another concurrent line, I can tell what's happening is this 1 and this 1 get split into 2 each. So that adds, we had an old one, we get one new one. We had an old one, we get one new one. So it always adds 2 new. So this is 10, 12, all the way over to here. So, we could think about this as a linear sequence, being that we're adding 2 every time, or we could just look like a numerical pattern. So given this number, how do we get to there? So given 2, how do we get to 4? Given 3, how do we get to 6? Given 4, how do we get to 8? I realize here that the pattern is 2n. Okay, without knowing anything about linear patterns or y equals mx plus b, just seeing an easy pattern from 5 to 10. Okay, however, the way you would do it with a linear pattern is you would say, oh, look, every time I'm adding 2, so then there must be some number of 2's that I added. So we'll say like plus 2x, where x is the number of 2's we've added. And then we start at some starting value. So let's see. So if we've added 1, 2, that's plus 0 because the answer is 2, right? So if I plug in 1 here and go 2 times 1 is 2, then add 0. And then we try it with the next one. So 2 times 2 plus 0 is 4. Hey, that checks out. So our y equals mx plus b was a y-intercept of 0 and a slope of 2. And we got 2x or 2n. All right, let's do the next one. What about how many regions do 35 parallel lines in a plane divide into? Okay, so to start, it's 1, 2. So I'm going to make, for number 2, a little table. So for 1, 2, 3, 4, 5, etc., So if there's one line, there's 2 spaces. If there's 2 lines, there's 1, 2, 3 spaces. If there's 3 lines, there's 1, 2, 3, 4 spaces. If there's 4 lines, there's 4 lines, that's 1, 2, 3, 4, 5 spaces. And so you see the pattern. You're adding 1 each time. Again, you got 2 ways to do this. You can say, how do I get from this number to this number each time? Oh, well, it's an obvious, for n, you get an n plus 1. Oh, it didn't answer up here. For 35, the answer would be 70. Okay? And so then over here, if we have 35, the answer down here would be 36 for this one. If we were looking at it in terms of a linear sequence, we would say, well, each time we're adding 1, so there's some number of 1's being added, and then we just plug in this value and say, well, starting at 1, that's 1 times 1. Okay, that's 1. How did we get to 2? We added 1 there. For the next one, let's try that out. Let's see if our equation is 1 plus 1x. Oh, a little pop-up. And so let's see if that works, okay? So if we plug in 2, we go 1 plus 1 times 2. So plugging in the 2, seeing if we get 3. 1 plus 2 is 3. Hey, yeah. So again, our y equals mx plus b here, the slope was we changed by plus 1 each time. And then our y-intercept, we found we needed a plus 1 there to add on. Because if all we did was the 1x, we would just get 4, and we would just get 3. So each time we had to add 1 to it. So you could think about it as a linear sequence or just as what pattern do you recognize? Okay, so for number 3, it says, how many diagonals can you draw from one vertex in a polygon? Okay, so it already gives us the first one. So it says if we have 3 sides, you can't have a polygon with 2 sides. So we start at 3, and then we go to 4, and then 5, and then 6, and then 7, and we'll see what pattern we get. So there are no diagonals in a triangle. This is a side, and there's no other point. So we get 0. And then if there's a 4-sided thing, we pick a vertex. There's a side, and there's only one diagonal, okay? And then we say for the next one, from this vertex, there's a side, and 1, 2 diagonals we could draw from that vertex, so 2. So I'm thinking if we draw a hexagon here, 6 sides, and pick a vertex, we go side and side, so these don't count. And then we've got 1, 2, 3 diagonals we could draw. And sure enough, the pattern is holding, so it's going to be 4 after this. So again, we could look at, this time I'm going to start with the linear. I'm going to say the slope here is we're adding 1 each time. And so this is a y equals 1x plus some starting value. Well, let's plug in 3 and see what we get. So we go, we should get 0 when we plug in a 3. And so what's the y-intercept there? Well, that's 0 equals 3 plus b. So b must be -3. So we think our equation is y equals 1x minus 3. Okay, let's check it with the next one. If I plug in 4, so 1 times 4 minus 3, that's 4 minus 3, that's 1. Hey, that's what we got, right? So the other way you could have noticed is how do I get from here to here? Subtract 3, subtract 3, subtract 3, subtract 3. So if I have an n here, then it's going to be n minus 3 as the number of diagonals you can draw from that vertex, right? And for 35, the answer is going to be 32. Oh, did I do that up here? Yeah, I did. Okay. What about the total number of diagonals in a 25 or 35-side polygon? Okay, so we could do it either with a pattern or we could build on previous information, right? So we'll look at it both ways, okay? So for this one, we'd say, all right, well, let's set up our table. Okay, so we start with 3. If there's 3 sides, we have 0 diagonals. If there's 4 sides, there's 2 diagonals. If there's 5 sides, it's going to be hard to count. So 1, so I'm just going to trace it. 1, 2, 3, 4, 5. So there were 5. For 6, it's going to be harder to count. So let's do this. Okay, I'm going to do them in pink. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. So we've got 9 there. Okay, did I miss one? I think I missed one. I have the hardest time counting. So for this one, it was 3. For this one, it was 3. For the next one, we already have this diagonal drawn, so there were only 2 new ones here. And for the next one, we already had this diagonal drawn, so there was only 1 new one that you could draw. And then for the next one, could you draw any? No, you already had diagonals here, here, and here, so there were no new ones. So it was 9. Okay, then let's look at, what about for a 7-sided figure? Because here we added 2, and then here we added 3, and then here we added 3. So this is an interesting pattern so far. So let's go to 7, okay? So that's 7, right? 1, 2, 3, 4, 5. That's 6. Oh my gosh, counting is so hard, you guys. Okay, 1, 2, 3, 4, 5, 6, 7. All right, so I'm going to do it in blue here, okay? So from this one I could do, right? So if there's 7 sides, I could do 1, 2, 3, 4, right? So I can't connect to the 2 next to me or the point. So out of all of the vertices, the 7 vertices, I could connect to 4 of them. Okay, and on the next one, I could connect to 1, 2, 3, 4, right? The same thing. And then, for the next one, there's already a diagonal drawn to it. So of the 4 diagonals, there's only 3 new ones left. Okay, for the next one, so I could draw on 1, 2, 3. And then for the next one, of the 4 diagonals, 2 are already drawn. So there's only 2 new ones. So I'm going to draw it. And then for the next one, of the 4 diagonals, there's 3 already drawn. So there's only 1 new one, and it's this one. And then over here, all 4 are already drawn, so there's 0 new. All 4 are already drawn, there's 0 new. So you get 4 plus 4 plus 3 plus 2 plus 1. So that's 14. So we add plus 5 there. This is a crazy pattern. Plus 2 plus 3 plus 3 plus 5. What's the easy pattern here, right? I don't see something. Let's do a number 8 here. All right, so that's an 8 there. So now we say, okay, well, we've got from any vertex, we can't connect to the sides or itself, so we've got 5. Then the next one, same thing, we've got 5. And then each vertex is going to have 1 less. So for this one here, there'll be 4 because I will have already drawn this one, right? And from the next one, 3 because I will have already drawn both of these. Then 2, then 1, then 0, then 0. So what we end up getting is 20. And so we get, whoops, I wrote, so 8 and 20. So we get plus 6. This must have been, oh my gosh, that was the reason. It was a plus 4. So what's happening here is we're now adding by 1 more. So this is going to be a quadratic sequence. And I know that because the difference of the difference is the same every time, a second tier. So what that tells me is that we have an x squared plus x plus number kind of thing. Like, for example, something like this, where this x squared is controlling this second level difference. Now, how to do a quadratic is kind of hard, so let's instead use what we already knew, right? So we already knew that from any one diagonal, you could draw n plus 1 diagonals from the, oh, that's 2. For 3, you could draw n minus 3 diagonals to each one. Okay, so let's think about that, okay? So what I'm going to do here is I'm going to erase some of this work here. Okay, or actually I'm going to do a better job by just circling it and deleting it. Okay, so what we know then is if we have 6 vertices, whoops, that's not 6, counting. Okay, so if we have 6 vertices, then each one of those, so n vertices, can make n minus 3 diagonals. Okay, so we get n times n minus 3 diagonals. Although there's a problem. That means from here I could draw n minus 3. And from here I could draw n minus 3. We are now counting every diagonal twice. We're counting it as being drawn from both endpoints. So actually we have n times n minus 3 as the number of diagonals we could draw. But then we have to divide it by 2 because we're drawing once from the left and once from the right. And we don't want to count every diagonal twice. So we divide it by 2. Let's just check. Let's plug in 8. Okay, so 8 times 8 minus 3 over 2. That's 8 times 5 divided by 2. That's 40 divided by 2. That's 20. Check. Let's do 7, okay? 7 times 7 minus 3 over 2. That's 7 times 4 divided by 2. That's 28 divided by 2. That's 14. Check. And so if I were to multiply this out, so the answer here then for n is n times n minus 3 over 2. Okay, and I can plug in for, oh no, this isn't, yeah, this is. So for 35, how many are there? But then I can separately multiply this out if I wanted to and see that it's a quadratic distributing. I get n squared minus 3n on top over 2. So our quadratic would be 1/2 n squared minus 3/2 n plus 0. So that was the quadratic, which that would have been hard to kind of find by yourself. And so instead, building on that previous knowledge and going, how many diagonals can I draw from each one? Times the number of diagonals. But since I'm counting each one twice, I just divide it by 2. Okay, so last thing here, I'm just going to plug in 35. And I'm going to say, well, what the heck is 35? That's 35 times 35 minus 3 all over 2. Or in other words, 35 times 32 over 2. Or 35 times 16. And I do not know what that is off the top of my head. Let's do it on the old calculadora. Okay, I gotta pull out my calculator for this. 35 times 16, that's 560. Ooh, that was a lot of work for that problem. Okay, let's do the next one. So if you place 35 points on a piece of paper so that no 3 are on a line, how many line segments are there? Okay, so, well, if we plug in 1, we get 0. If we plug in 2, there's 1. If we plug in 3, there's 3. If we plug in 4, there's 1, 2, 3. Okay, 4, 5, 6. All right, let's do one more just for the sake of it. So for 5, you have basically the same as last time, right? You have all the diagonals, but now you have the number of sides added in. So one thing you could do is build on the last one, or we could do it totally different, okay? So from 5, we knew there was already 5 diagonals, right? There's 1, 2, 3, 4, 5 diagonals, plus the 5 sides, so that gives us 10. So let's look at what we have here. If we look at pink, we go plus 1, plus 2. All right, this goes up by 3, and this goes up by 4. So even though it's changing each time, I do notice that the acceleration here, the rate at which the speed is changing, is staying the same. And so that means we've got that quadratic again. So again, I'll teach you down below later in this video how to do a quadratic, like kind of manually. But however, in this scenario, what we can do instead is say, okay, let's say we have 100 points, right? Well, then I could say, okay, well, the answer is, the way we can connect them is from each of the 100, so we have 100 points, we can multiply it by how many each point can do, right? So each of the 100 points could connect to every other point. Doesn't matter if they're next to or not. So if there are 100 points, the point can't connect to itself to make a line segment, because that's not a line segment, but it can connect to every single other one. So it's 99. Or in general, if you have n points, you can connect to n minus 1 other points. Now, some of you may have noticed, though, what that means is I'll connect this way, and then when I am counting this point, saying how many can it connect to, I'll connect backwards. And so what we've exactly done is connected every single thing twice. And so what we need to do in the end is divide it by 2. Right? Because we're saying each one can connect to every other one but itself. So there are n points, and each one connects to n minus 1. So n times n minus 1 is every connection. But what we've done is we've said this one connects to 2, and this one connects to 2, and this one connects to 2. And so we've connected 2 times for each line, one going forward and one going backwards. So in the end, we divide by 2. So the formula here is n times n minus 1 divided by 2. Let's try it. Okay, so 2 times 2 minus 1 over 2, we should get 1. So let's see, we get 2 times 1 over 2. Yup, that worked out. Let's try it with 4. So 4 times 4 minus 1. So that's, divided by 2. So that's 4 times 3 divided by 2. That's 12 divided by 2. That's 6. And sure enough, that's what we got. So for n points, we get n times n minus 1 divided by 2. And for 35 points, we get 35 times 35 minus 1, or 34, over 2. And I don't know what that is. We'll just smash that into a calculator. Okay? And then down here, you go, if you draw 35 lines on a piece of paper so that no 2 lines are parallel to each other and no 3 lines are concurrent, about how many times will they intersect? Okay, well, we can exactly do that. Let me pause for 1 second. Okay, so let's think about this, right? So if we have 1 line, how many times will it intersect? 0. If we have 2, how many will it intersect? Well, that's 1. If we have 3, then how many will it intersect with? Well, we can see right there it's 3. And then if we have 4, so really we're just saying if we add a line. Well, think about it. If I add a line to the first one, it is not going to be parallel And it says on a piece of paper, so they're in a plane, and no two lines are parallel. So that means they can't be parallel and they can't be skew. So this line that I'm drawing will hit every line in the plane because they're all on the same plane and they're not parallel. So if I draw a line and there's already two, I will hit 1, 2. If I draw a line over here, it will for sure hit 1, 2, 3 because they're not parallel and they're on the same plane. So if I do a fourth one, it is going to hit, right? This added 3 points of intersection, this added 2 points of intersection. So we will now add 4 new points of intersection. And then the next one will add 5 new points because there will be 1, 2, 3, 4 lines. So when we add the fifth line, it will 1, 2, 3, 4 hit. And then when we have 1, 2, 3, 4, 5, and we add the next sixth line, it will go 1, 2, 3, 4, 5. It will hit 5 new points. So we get, when we go to 5, this was, right, so it's +1, +2. This was supposed to be +3. I don't know how I added 4. I don't know what I did there. Sheesh, I'm getting rusty here. Okay, so we added 3 new points of intersection of 4. We can literally count them. 1, 2, 3, 4, 5, 6. There are 6 there. The next one, we said, hey, we add 4 new points because that fifth line hits the 4 existing lines. So we add 4, and we get 10, and then we go to the next one, 6. We added 5, so we get 15, and so on and so forth. And again, the second tier, the difference of the difference, is staying the same. So we know this is a quadratic. But again, we can think about this by saying, okay, so how many lines do I have? I've got 1, 2, 3, 4, 5, 6 lines, right? So each of those 6 lines can hit how many others? They're not parallel, so it has to hit 5. So for all 6 lines, it will intersect the other 5. If there were 100 lines, each of the 100 lines would hit every other line because they're not parallel and they're in the same plane. So 100 line times 99 intersections, right? So in general, n lines will intersect n minus 1 lines, right? Each line will hit every other. But just like on the last one, just like where we said, we're not going to count the line segment forward and the line segment back. It's the same line segment. We don't need to count it twice, so we had to divide by 2. Here, same thing. If I have a line and it hits this other one, that's not 1 intersection and 2 intersections, right? We don't count it twice because 2 lines, like, hey, line A hit the other, that's 1. Oh, by the way, line 2 hit that one, so that's 2. No, we just say that's 1 intersection. So wherever 2 lines meet, we get 1 intersection. Wherever 4 lines, however many they hit, we don't count them twice, we divide by 2. So in the end, we get the same formula as the last one. For the nth term, it was n times n minus 1 over 2. And so whatever we got for that last one for 35, we just do the same thing again. So here the 35th term is 35 times 34 all over 2. All right? And then, so each team in a 10-team league plays each of the other teams 4 times in a season. How many games, or how many league games are played during one season? What geometric figure can you use to model turns played? So again, I'm going to see this as like, there are 8 teams here. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 teams, okay? And what we're going to do is we're going to say, okay, so how many games will this one play? So from this point, so 8 points, and how many games will they play? Well, they will play, right? How many per? Well, there will be 7 other teams times 4 games each. Right? So we'll get that many games in total, right? So this one can do 28 games, and then this one can play 28 games, and this one can play 28 games because they'll play every other of the 7 right? There's 8 teams. So this one of the 8 teams will play the other 7 each 4 times. So that's 4 times 7, that's 28. So every single of the teams will do 28. So we just multiply it by 8. So we say each team plays 28 games. There are 8 teams, so we get 8 times 28. However, again, we don't count games twice, right? If 2 sports teams play each other, 2 games didn't happen. Sure, they each played a game. However, we don't count it twice. So whatever we do in the end, we have to say, well, since we counted 28 games for each team, and they weren't playing anyone else, they were playing each other, in the end we divide by 2. Because whenever 2 teams played, we counted it for both. We said, hey, the Eagles had this many games. Oh, and the Broncos had this many teams. So in the end, we go, but we know they played each other, and we counted it twice. Once for the Eagles, once for the Broncos, for sure. Every game got counted twice. So we divide it by 2. So the answer is 8 times 28 divided by 2. And I used a nice octagon for this. And it was really the same problem as this one. If we have all the different points, how many ways in which can they, intersect with each other? The only difference was whatever the answer was, we just multiplied it by 4. Because there was not just one segment connecting each point, there were 4 segments connecting each point. So it was the same answer as this one. We just literally went times 4, times 4, times 4, times 4. That was the only difference when we moved down to the 8 teams. All right, last one here. If a person at a party shook hands with everyone else at the party exactly once, and there are 66 handshakes, how many people are at the party? So again, this is that same problem, right? So let's say there were 100 people at the party, right? 100 people, how many handshakes does each one do? If they shake hands with everyone else exactly once, they shook hands with the other 99 people. Right? So that's how many handshakes took place. For every person at the party, they shook hands with n-1 people. And yet again, we don't count handshakes twice. If Bob shook Sue's hand and Sue shook Bob's hand, that's only one handshake. So in the end, we double counted everything. So we just divide by 2. Okay, so our formula for number of handshakes at a party is this. But the question now is, what if n times n-1 over 2 is equal to 66? So we got a couple ways to do this. One is just guess and check. Be like, I don't know, 10. So 10 times 9 over 2, that's 90 over 2. That's 45. That's not enough handshakes. What about 12 times 11 over 2? That's 132 over 2. That's 66. Oh, guess and check worked. There were 12 people. However, guess and check's not a great method, so instead let's solve the equation using Algebra 1. So I'm going to just get rid of the fraction and the parentheses to see what we're dealing with here. So I'm going to multiply both sides of the original equation by 2. So I get n times n-1 equals 132. Then I'm going to multiply out to get rid of the parentheses. So we got n squared minus n equals 132. And now we go, oh, look at that. I got a quadratic. So I know my strategy to solve a quadratic is move everything to one side, where the n squared term is positive. So I get n squared minus n. Now minus 132 equals 0. Okay? The next step is to factor and get 2 things that multiply to make 0. And that's our overall plan whenever we get a quadratic. So first we just cleaned it up to see what we had. And we know we got a quadratic. So everything to one side. Now we want to factor it. I use the Xbox method. There are absolutely shorter methods. So first times last. Whoops, that's negative 132. And then the middle term. Okay, and so what we're trying to do, I just like using numbers instead of the variables. So what we're trying to do is get something that 2 numbers that multiply to make this and add to make this. Okay, so I know if they multiply to make a negative, one is negative and one is positive. All right, and so what I'm going to do is I'm going to go down and go, well, is it 1 times 132? No. 2 times 66? No. 3 times 44? Oh, I'm getting messages here. 4 times 33. 5 doesn't work. 6 times 22. I love these 11s. This is nice. 7, I don't think works. Nope, doesn't work. 8 times. So there's only so many things. I only need to go up to check at about 11 or 12, and that's it. And I could use a calculator for this just to see if they work out nicely. So let's see if 8 goes in nicely. So no, it does not. Okay, let's see if 9 goes in nicely. No, it does not. Let's check 10. Nope. Let's check 11. Oh, times 12. Oh my gosh, that's our winner. They're 1 apart and their difference. So I know there's more negatives. So this is a 12 and an 11. And if that wouldn't have worked out, the next one we would have gotten is this. And we're counting the same thing again. So we're done. And if it wasn't one of these 6 options, we'd say that's it. There, you can't factor it. And then we'd have to use the quadratic formula. But we could factor it. So over here in the box, you put the first term and the last term. And then the whole goal was to split up this middle term, and now we know how it was split up. We know that it was originally a negative 12n and a positive 11n. And now we just factor out the GCF of each row. And I have a video about how to solve quadratics if you don't know how to solve it. I think it's at the beginning of my geometry playlist here. Okay, so let's factor this out. N, this one would be negative 12n. Nope, just negative 12, sorry. This would be n, and this would be 11. So we get n minus 12 times n plus 11 equals 0. And the only way two things can multiply to make 0 is if this one's 0 or this one's 0. That's the only way, right? There's no other way to multiply to make 0 unless one of the two things or both is 0. So either n is 12 or n is negative 11. So were there negative 11 people at our party? Probably not. That doesn't really make sense. Let's cross that one out. So there were 12 people at the party. So it was exactly what we got with our little guess and check. And if the number was any bigger, like if the number was 500, I would not have guessed and checked. I would have solved it. But it was just because it was just such a small, like tempting number. I was like, I could probably get that in a few guesses. All right, so let's just review how to find nth term of a generic sequence. You don't have a picture to reason out, like there are 100 points, each one's connecting to 97, what's the pattern? Instead here, you just got a sequence. Well, either it's something to do with addition and subtraction, or it's multiplication and division. Okay, if it's addition, that's the first thing I check. I go, okay, well, let's see what got added. Okay, oh, well, look at this. Everything you're adding is the same each time. So what that tells me is, in our y equals mx plus b of our straight line linear, it's going at a constant speed. And so every time you go right one, you are adding 2, right, or 2n, to x. We just don't know the y-intercept. So we know that we have some number of 2's, okay? 2 times n, right? There's some number of 2's. And it gets bigger each time. We add one more 2, one more 2, one more 2, one more 2. What we don't know is what was the starting value. So if I plug in 1, right, here I get 2 times 1, plus what would give me 1? Oh, minus 1, right? So that would give me what we want. Let's try it out. So plug in 2 here, and I go 2 times 2 minus 1. So that's 4 minus 1, that's 3. Heck yeah, that worked. Another way to do it, now we don't need to go down a rabbit hole. I like to do it like y equals mx plus b. So I just know the slope, and then I just plug in any single point. You could say the third term was 5, so plug in the third term equals 5 and solve. 5 equals 6 plus b minus, we get b equals negative 1. So the end result is we get y equals 2x minus 1. That's the equation for it. Or you could say the nth term. So if I plug in the n here, what I get coming out is 2n minus 1. That's the nth term of this sequence. Okay, let's do it again. So here, I'm going to see, what's this pattern? Let's see, we minus 3, we minus 3, we minus 3, hey. So that tells me the slope is minus 3. Or you could say there's some number of minus 3's. All you don't know is, what was the starting value? And really, another way to get to the starting value, like on this last one, is just take a step backwards and say, what was the 0th term? What if I had no plus 2's yet? What did it start as before I added the first plus 2? Well, it started as negative, I'm going to erase this little example here. Before we started, it was -1. And then we plussed 2 to get to the first term that had 1 plus 2 in it. And so we got the number of 2's plus the -1. So down here, one quick way to get the starting term is to just see what was I at? Oh, it was 11. So I know it's -3n minus 11. That's a quick way to do it. Or you could say, I know the slope's -3, and I'm just going to plug in any point. So here's first, second, third, fourth term. Let's do the fourth term. So when I plug in, when I plug in 4, out should come the result of -1. So let's see what we get. -1 equals -12 plus b. We add 12 to both sides, and we get b equals 11. Oh, why did I write -11? This was a positive 11. Silly me. That was a positive 11. See, double checking your work is helpful. And you could plug in one more and just see if I get the right thing. So -3n plus 11. I plug in 3. So the third term of this sequence is -9 plus 11, 2. Sure enough, that worked out. Okay, let's do one more. Here we go. We are adding 5. We are adding 5. And so, where did we start? We know this is a y equals 5x plus something. Or you could say I have some number of 5's. And then I just go, where did I start? What was the 0? What was the 0th term, right? It was 95, right? Or just plug something in 1, 2, 3. So let's just plug in the 2. So we just get, if I plug in 2 and add b, I should get 105. And so you just go, oh, well, that's 105 plus, equals 10 plus b, subtract the 10, b is 95. So our equation is y equals 5x plus 95, or 5n plus 95. So that's a linear equation. Okay, what if we got a geometric one? This is the same idea, but on a different meta level. And the last one will be quadratic. So this one, you go, plus 9 plus 90. I don't know what's going on, but you go, wait a second. My second thing I could try is a times 10, times 10, times 10. Okay, so here's another way to do this is you go, oh, so I'm multiplying by some number. So when you're adding, like plus 5, plus 5, plus 5, that's 5 times 3, right? So we said, well, we have some number of 5's. That was the old version. However, now what we've got, let's scratch that out. Let's just move it up here. So that's the old, right? That's that's addition. Okay, that's no good. That's not what we want. I want to say times 10. Man, my iPad is melting here. It does not like how much work I'm making it do. Hold on one second while it wakes up. Okay, there we go. So this time, if you times 10, times 10, times 10, that's 10 to the third power. That's how many 10's are we multiplying by. So here we got times 10 to the n power. And again, we just simply need to know what was the starting value here. And the easiest way to get it is go, what was the 0 term before we multiplied? And so that would be, in this case, we divide that by 10, we get 1/10. So that was it, 1/10 times 10 to the n. Another way to write that would be 10 to the n over 10 to the 1, or 10 to the n minus 1. That would be a simpler way. Okay, I'm just going to do two more quickly, because this isn't something we're doing in this class. So here you multiply by -2, multiplied by -2, multiplied by -2. So I'm multiplying by some number of -2's. And what did I start at? So here's my 1, 2, 3. What was my 0th term? So if I multiplied by -2 here, then I must have started with a -3. So -3 times that. And we can just double check. Let's try one, okay? So if I plug in 2 here, so -3 times -2 to the second power, that's -3 times -2 times -2. So that's all of those negatives end up with a negative. And 3 times 2 times 2 is 12. Hey, that worked out. So there's our equation. Do that again. So times 3. Whoa, that's not times. Times 3. Times 3. So I'm multiplying by some number of 3's. And what was my starting term there? Well, it was, so if I divide by 3, that was 4/3. So it's 4/3. thirds times that. And we could clean that up if we wanted to. I'm not going to. I'm just going to leave it like that. So that's kind of how to do geometric scenes. It's the quadratic, though, that we're interested in. So on this one, we go, we add 5, we add 7, we add 9, we add 11, and so we go, shoot, they're not the same. However, we do notice a pattern. We're adding 2 each time. So what we know is this is a quadratic, and what you do is if we have an squared plus bn plus c, and we want to find the a term, this is half the second difference. Okay, and this is kind of something you can just take from me. The y is really cool. The calculus is interesting. In terms of an Algebra 1 explanation, I don't have like an Algebra 1 explanation in terms of why it's half the difference. The calculus is really beautiful, but yeah, the y there is not a really simple explanation. So in this case, the second difference is 2. So then we know we have 2 divided by 1, or 1 n squared, plus, and then we don't know how many n, and we don't know this starting thing, okay? So now what we need to do is go, well, if we know we're adding a 1n squared, let's just take away the 1n squared. So here's where we write, that was the original, and then what we're going to do is, I don't know, maybe in orange, I'll write the n squared. So that 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So what we do is we subtract this from every value. And what were we left with? So if we just take the n squared out, we're left with a linear equation. So we just subtract the n squared completely out. We know the half the difference, so we got this n squared term. So let's just get rid of it now. Okay, so now the original sequence becomes, we take away 1, we get 5. Take away 4, we get 7. Take away 9, we get 9. Take away 27 minus 16, that's 11. And then we get 13. And look at this. Now we have a regular old quadratic plus 2, linear, plus 2, plus 2, plus 2. And so down here we go, oh, that was 2n plus. And remember my trick for 1, 2, 3. I just go, what was the 0th term before we added 2? The starting value was 3. So 2n plus 3 is that last sequence. So in the end, we get n squared plus 2n plus 3. And we can just double check. Let's just plug in 4. So we get 4 squared plus 2 times 4 plus 3, 16 plus 8 plus 3. That's 24 plus 3. That's 27. Okay, I'm going to do one more problem, and that'll be the end of the video. So we'll go plus, hold on one second, I'm going to pause. Okay, so I'm going to go plus 7 plus 13 plus 19? Is that right? 19? Yeah. And so let's see. So that wasn't linear. Dang. But let's see if there's something going on here. Plus 6. Plus 6. Hot dang, it is. Okay. So remember, the n squared term is half the second difference. So we take this and we go, that means we have a 3n squared plus some numbers of n plus some number, right? So we can figure out the linear part. All we got to do is subtract that 3n squared. So we have the important stuff. Okay, so what's 3n squared, right? For the 1, 2, 3, 4 terms. So 3n squared would be 1 squared times 3 is, I'm going to move that over a little bit. So 1 squared times 3 would be 3. 2 squared is 4 times 3 is 12. And then 3 squared is 9 times 3 is 27. And 4 squared is 16 times 3 is 48. Okay? So now we're going to subtract that and see what we get for the original linear sequence now that we get rid of that. Oh, again, my iPad is freezing. Come on, iPad. It's the last problem. There we go. Okay. So I subtract 5 minus 3. I subtract 12 minus 12. 25 minus 27. 44 minus 48. So we just take away the 3n squared, and this is what we're left with. Well, I can tell right away, this is a common difference. It's just subtracting 2 every time. So in terms of a y equals mx plus b, this is y equals negative 2x plus, and then again, I just do what was the starting term, right? Here's the first, second, third. The starting term was 4. So it's negative 2x plus 4. So negative 2n, that's a 4. So last thing I'll do is just double check. You should always do it. Let's do it with the 3. Okay, so 3 times 3 squared plus negative 2 times 3 plus 4. So that's 27 minus 6 plus 4. So that's 21 plus 4. That's 25. Exactly what we were hoping for. So our end result was 3n squared minus 2n plus 4. All right, you guys, I hope you enjoyed that video. Longer than I planned.